welcome everybody, the panelists and the participants, to this second event, organized by the Middle East and South Asia Meetup Group, which is founded by myself, and there are 6 other co-founders. One of them is Minerbi, who's also a speaker today. We're delighted to have him. I should also mention that our sponsors are our friends at Washington, D.C. Quantum Meetup Group. Dr. Dave Ghoshal, who's one of the participants today, has very kindly agreed to sponsor us, together with Association Quantum, who actually sponsor their events as well as Cambridge Quantum Computing, which works with Association Quantum. So that's a brief intro to what's going on today. We have 2 wonderful moderators with us today. My good friend Dave De Silva, who is also the Chief Operating Officer of Darkstar Quantum Lab. This is a startup company that I am actually affiliated with. The CEO is David Wilkinson, and we're lucky to have Dave as our wonderful, manager, if you will, hands-on manager who takes care of everything in his capacity as Chief Operating Officer. We also have Hanin Abu Alrub, who I am very proud to admit or state that she is a former student of mine from Khalifa University. She's right now situated in Abu Dhabi, where Khalifa University is. And Hanin and I had some good times, when she was my student of game theory. It was a pleasure, having her in my class, a bright student, bright individual, and a budding game theorist. So with that introduction of the moderators, I'll pass the mic to Dave De Silva and Hanin, and please introduce our speaker and take it away, Dave.
Well, thank you very much, Faisal. And Hanin and I are very happy to be co-moderators. This is the first time that we're co-moderating. We have been working for a little bit, the 3 of us, in fact, more with David Wilkinson on that high frequency trading application, for which we think your software has to do with portfolio optimization and quantum computer aided design, which we're very excited about, and we'll be talking about those things. Hanin, this is your first time as a moderator, period. Is that correct?
Yes, actually, it's my first time, and I'm really excited. Like the adrenaline is flowing everywhere. So yeah.
Well, that's wonderful. What we're doing here, ladies and gentlemen, is recognizing and bringing in those who are new to the quantum computing meetup world. And Hanin, you're a budding star. You've been trained by Dr. Khan. Dr. Khan is also the chief science advisor of Darkstar. And Nir is the CEO of Israeli startup Classiq, which is exciting. And we'll talk about Nir's background in just a moment. So Hanin, what we're going to do here is I'm going to do my best to work with you and have an interactive session with Nir as we had gotten together on Friday, and we're going to try and do our best to make things fun with and educational without interrupting Nir's flow. You still good with that, Nir? Oh, fantastic. So this is the first time we're doing this together. And what we could do is when we have a question, or a comment, we can do that. And when you feel fit, Nir, you could pass the mic to us by just acknowledging us, and we can say something. And Hanin, I'll take responsibility for moderating, because we're both excited and we don't want a conversation that may naturally come about to throw Nir off for what he's doing. So I'll take responsibility for and blame me if we get too excited and keep going into things. And Nir, what I'll ask from you is if we're talking too much, just put your hand up. And then that's my signal to pass the torch back to you. Dr. Faisal Shah Khan, thank you for requesting from the audience to ask the questions through the Q&A. There's also chat. Faisal, I'll rely on you to let us know when there's questions. If you do the same thing, that's going to be helpful. And in fact, we'll rely on you to filter the questions and to pose them. And I think that would be a nice approach. Is everybody happy with that approach? Yes. Okay. That okay. It's wonderful.
Absolutely.
Oh, that's so nice. Hanin, maybe a few more words from you, and to how about if you introduce Nir? We were very excited when we looked at his background. We're very proud for what he represents in the world of quantum computing. And are you good right now, Hanin, to talk a little bit about Nir?
Yeah, of course. So I've been waiting to talk about Mr. Nir. So first of all, I'm really happy I'm co-moderating this event and reuniting with Dr. Faisal. So as he said, I had the honor of taking game theory with him, and I learned way more than just game theory in that course. And I was also introduced to quantum computing with him. And so that's why I'm very excited. And also Dr. Faisal is host of the MESA meetups. So there are other series, of course, for the meetups. And I also met with Mr. Nir last week. And there I was introduced more to his background and what he does. And honestly, I was really inspired by him because he finished his master's in 2018 in electrical engineering. And then he founded the company in 2020. So it was like a direct shift. So he decided to start his own company. He didn't just go and follow the regular routine. He wanted to be the CEO, and of course, of a very classy and classic company called Classiq. See what I did there, Mr. Dave? So yeah, so Mr. Nir will talk about his company and also the past, present, and future of quantum software development. So Mr. Nir inspires all of us, and I can't wait to hear your talk, Mr. Nir.
Great. Thank you so much, Hanin, David, and Dr. Faisal. It's a great pleasure to meet you all, and thank you for everyone that is viewing us right now. Great. So let's dive into quantum software, right? That's the right time. Perfect. So let me share my screen for a moment. Do you see it right now?
Yes.
Yeah, perfect. So let's go. So what we're going to do is to talk mainly about quantum software development. We'll start a little bit of how to program a quantum computer, right? What's the basics, how it's being done. And then we'll go through the past, the present, and the future of quantum software and algorithm development. Right, so basically, I'm not going to talk about the hardware almost at all, but let's start with the hardware anyway, just for 2 minutes. So in the last few years, we see, what some are calling quantum revolution. And the main part of this quantum revolution is the hardware development. And we see many of the tech giants led by IBM, Microsoft, Google, Intel, now Amazon, Honeywell, and many fantastic startups like PsiQuantum and Rigetti and IonQ. So they're trying to develop the first useful, practical quantum computer. The goal is one, right? But there are many ways to go and many ways to implement the qubits, right? The quantum computers. So most of the giants today, Intel, IBM, Google, Amazon, they are going on superconducting qubits, but some are trying to produce photonic qubits and silicon-based, and Microsoft has a very different way of topological qubits. And that's great because, you know, for the software ecosystem, we need only one winner, right? So it's great that there are many hardware providers, and hopefully, and you know, it seems like that the progress is amazing. In the next few years, we'll see the first occasions of quantum advantage. Right, so now let's dive a little bit into the basics of quantum software. First thing that should be understood is the computer is quantum, but the interface is classical, right? You don't need to have a quantum computer in your basement because you can access it via the cloud. The input and the output of a quantum computer are classical, are bit strings in between. So yeah, here is the quantum computation, and we'll dive into this part, but the interfaces are totally classical. Right, so the very basic building block of a quantum computer is the qubit. Like in the classical world, we have the bit, which, you know, in any moment is a 0 or 1. So a qubit is, as you all know, at the same time a 0 and 1, and actually it's it can be on any place on the block sphere, right? And we'll dive into that in a few moments. Right, but now we want to understand it in a more concrete way. So how do we represent a qubit? So one qubit is represented by a vector, right? A1 is the probability of the qubit to be measured as 1. A2 is the probability for it to be measured as 0, and A2 is as 1. And you see that the powers of the probabilities are summed into 1. But now let's talk about 2 qubits. So if we want to represent 2 qubits, so we have 4 options, right? 0, 0, 0, 1, 1, 0, 1, 1. So again, the probability of the 2 qubits to be measured as 2 zeros is B1. And again, the probabilities are summed to 1. Great, so that's the representation. Now, before we dive into the math and logic and the the quantum software programming languages, let's understand for a moment the sources of power of the quantum computer. So first is superposition. We have just talked about that. A qubit is at the same time a 0 and a 1, and 2 qubits are at the same time in 4 states, and 300 qubits are at the same time in 2 to the power of 300 states, which is huge, obviously, right? So great, we have this parallelization of computation, but we need to access that. We need to do something with that in order to measure in the end of the quantum algorithm only one result. The other aspect is quantum entanglement. Quantum entanglement describes the very counterintuitive correlations between the qubits, which is very hard to understand, but when we look at the math, it's quite simple, and we'll do that in a few moments. The third part is quantum interference, because again, it's great that we have a parallelization of 2 to the power of 300 states, but finally we need only one result, right? So we need to be able to cancel on the non-interesting results and to remain with the result to an interesting problem, right? Great, so if we understand this slide, we understand the whole, the whole idea of quantum software, of quantum algorithm development. When we solve the Schrodinger's equation, we understand that in order to describe the development of quantum states for one state to another state, the logic is applying unitary matrices on the quantum state. right? So let's say we have a quantum state of n dimensions, of n particles, let's say n qubits. So the vector that describes it is in the length of 2 to the power of n. If we want to change this state and to achieve actually any other quantum state in the same 2 to the power of n dimensions, we can just write the unitary matrix of this size of 2 to the power of n on 2 to the power of n, and we can do that, right? But now there are two problems. First, this matrix is huge, right? If you want to apply this computation on 300 qubits, again, we can't even write this matrix. That's the first problem. The second problem is that even if we knew how to write this unitary matrix, we can't apply it on the hardware, because the hardware today, quantum computers today, can apply only 1 or 2 qubit gates. Otherwise, it's too noisy, right? So we need to decompose this unitary matrix into 1 qubit gates and 2 qubit gates, right? So for us today, that's the way to design quantum algorithms, with this 1 and 2 qubit gates. But what could be achieved with 1 or 2 qubit gates? So we said before that 1 qubit is, we can represent it on any spot on the block sphere. So in essence, what a single qubit gate allows us to do is to rotate the qubit to any other place on the block sphere. And in essence, if we are trying to understand what it allows us to do, it allows us to change the probability of the qubit to be a 1 or 0. If we take a qubit and start from 0 and we want to make a perfect superposition that the probability will be half 0, half 1, we can do that with the Hadamard gate, and we'll show it in the next few slides. And also we have 2 qubit gates, which allow us to apply entanglements and control operations on 2 qubits. Right, so now let's dive for a few moments into the math. So let's say we have a qubit that is initiated to be 0, 100% 0. And now we want to create a perfect superposition between 0 and 1. How can we do that? So we have the Hadamard gate, but okay, that's a quantum notation. Not all of us aware of what it means. So let's just do the math. Okay, it's really a relatively easy math. And what is being done here? We take a qubit. We see that the probability for the qubit to being 0 is 1. It can't be a 1 if measured. And we apply on it the Hadamard gate. We just multiply the matrices and we get this result. And we see here that there is a equal probability for the qubit to be 0 and 1. So we created a perfect superposition. So that's one example. Now let's get to a more complex example. Let's create quantum entanglement, right? Let's create the Bell state. So again, we start with 2 qubits that are both initiated to be 0. And now we want to create entanglement. We want the 2 qubits to be either 2 zeros or 2 ones. It can't be 0, 1 or 1, 0. So how do we do that? As we see here, we should apply an Hadamard gate on the first one, and then a CNOT gate on the second one. And here, if we multiply the matrices, we see that we have got a 2 qubit state, but that has probabilities only for 0, 0 and 1, 1. If we remember the qubit representation from this slide, right? 0, 0, 1, 1. Great. now let's move forward to more complex quantum algorithms. Right, so when we write quantum software, quantum algorithm, we need to use more than 1 or 2 gates, right? So that's a representation. That's a quantum circuit, and it's totally equivalent to quantum software. That's the way to design quantum software and quantum algorithms today. So in essence, what do we see here? We see each line is a qubit. We see here 7 qubits, right? So we remember that we could write this whole algorithm as one unitary matrix of 2 to the power of 7, which is 128 on 128. Again, we can't do that. We can't implement that on the hardware, and we can't think of that. So we write it with a 1 and 2 qubit gates. Actually, in this one, there are 2 Foley gates as well, but let's forget that for a few moments. So that's quantum circuits, which is totally equivalent to quantum software. Right, so now we understand the basics of quantum computation. We understand that if we know how to write the unitary matrix that will, transform our initiate quantum state into an interesting quantum state that will be that will solve a meaningful problem, we have found a new quantum algorithm, right? And we understand that we can't write it as a one unitary matrix, so we need to write it as quantum circuit, right? Okay, so now let's understand how quantum algorithm development was done in the 80s, in the 90s, and mainly in the past, right? Let's start from the past. First, who were the developers, right? So in the 80s and the 90s, and also in the beginning of this millennia, it was mainly done in the academy, right? Here you see some of the heroes of quantum computing, of quantum software. You see Deutsch and Simon and Grover and Shor and Harrow, Hasidim, and Lloyd, and some of the most genius quantum algorithms were developed by these people. But how did they do that? So actually, they did that without any quantum programming languages, right? In the 80s, in the 90s, there weren't any quantum programming languages. Actually, it didn't really seem like software. It seemed like algorithmic research, which was based on deep knowledge of linear algebra and the basic axioms of quantum mechanics. But when you take a look at the papers that were published, and we'll do that in the next slide, you see that equations, right? It doesn't look like software, and you definitely don't see any quantum circuits. The outcomes were mainly accurate algorithms and building blocks, right? Also scalable building blocks, the quantum Fourier transform, the Grover iterator, phase estimation, and of course the Shor's algorithm, the HHL algorithm, and some more. Not many more, obviously, but some more. Right. So here you see some of the most iconic papers, the Shor's algorithm, and here you see that's a linear algebra equation, right? You won't see here any hints for software, for compilers, for transpilers. They didn't have that, right? Also the Grover algorithm, and you can take a look at some of these other algorithms, and it was done mainly using linear algebra and the very basic quantum mechanics axioms. Right. Before we move to the present, Hanin, Dave, anything you would like to add so far?
Yes. So first of all, I really liked how you talked about the hardware from the point of view of superposition, entanglement, and quantum interference. We hadn't even talked about that, but I've been speaking with Dr. Khan previously that it would be really good if we talk about from the hardware point of view what quantum features are being activated. You've done a very nice job with that, and that makes me happy. Hanin, what do you think about that?
Yeah, I think it's great because even the audience, they were asking about those details. So I think it should be wonderful.
Oh, that's very good. So I haven't been monitoring that, Hanin. I'm glad that you have. Were there any other questions from what you read there in terms of we can ask Nir for more commentary, or do you think Nir covered it?
So I believe Dr. Faisal was answering. Meanwhile, so yeah, so someone asked for the names of the main quantum theorists, but I don't know if you want to readdress the question about having more than two Q states.
Faisal, you've popped up there. Do you have words of wisdom?
Yes, I think I'm going to go with the question Hanin pointed out. We have a question from one of the participants, attendees, which is asking about the names of the people who showed up on one of Nir's slide. So Nir, if you could briefly maybe scroll back to that and state the names for the audience, that would be great.
Yeah, for sure. So, well, I would love to be able to tell you which one is Simon and which one is Deutsch. They're both geniuses. I don't recall, so sorry for that.
I can help you with that, Nir.
Oh yeah.
So the picture on the left with the black sweater is Deutsche.
Okay, perfect. Yeah, right. So this is Simon and Peter Shaw, David Rover, Lloyd, Hasidim, Harold. Really, you know, these are the heroes of quantum computing, and you know, without the Shores and the Grover algorithm, I really don't know if we would see this quantum revolution of the last few years.
Mm-hmm.
That's a great question and an irrelevant question, luckily, right?
Well, before you go forward, Nir, I've been asked to type the names of these giants of quantum algorithms. So there was Simon. Do you know what the first name is of Simon's?
Don't recall, no.
No, okay. What about, who are the people in the two pictures on the top left?
Yeah, so this is Haro, Aram Haro.
Aram Haro, okay, yeah.
Yeah, something, Hasidim, I can remember the first Avinatan or something like that. And Lloyd, I can't remember.
Seth Lloyd, yeah.
Yeah, Peter Shore, Lev Drover. Yeah, these
Okay.
are the, yeah.
And so I think we'll go with that, and please proceed. I'll share this with with FW who had asked the question. Thank you so much, Nir.
Yeah, great. Right. So let's move forward to what is going on with quantum software today. So first, it's no longer only in the academy, right? In the last few years, so first we saw that the hardware providers started with IBM, and now of course Microsoft, Google, and Amazon starting, and others. So they are developing quantum software in-house. And what is maybe even more exciting is that in the last few years we see more and more enterprises joining this field and establishing quantum software teams that are trying to come up with the novel and game-changing quantum algorithms that will bring great advantage in the years to come. So that's a very partial list. Of course, we see large financial institutions and automotive companies, aerospace, pharma, energy, chemistry, etc. But obviously that's a partial list, and it's growing very, very rapidly. Right. So unlike the 80s and the 90s, today we have more development tools. right? We have quantum programming languages, we have SDKs like Microsoft launched and is really, useful. And we are in kind of an hybrid phase, right? Because on the one hand, the quantum software stack is still in its infancy, right? It's in comparison to the classical software stack, we are somewhere in the 60s, maybe 70s. But on the other hand, the progress is very fast. It develops fast. The outcomes of the last few years and these days efforts, first, the focus is mainly on NISQ algorithms or on noisy intermediate scale quantum algorithms. Mainly, you'll take a look on the papers published by these enterprises today. Many of them are around use cases of VQE and QAOA and some quantum machine learning heuristics. But the main goal is to achieve quantum advantage as soon as possible. Obviously, it's not possible today, but maybe in 2 or 3 years it will be possible. And what is very important is that the quantum software, the quantum circuits can be agnostic, right? When you write quantum software today, you don't need to dedicate it to a specific hardware. You can, and that's beneficial if you know, but otherwise you have these compilers and transpilers, which takes the agnostic quantum circuit and compiles it into a set of operations that will be applied on the actual hardware. Regarding end users, today it's mainly quantum information PhDs, mainly physicists, and obviously there aren't many of them, right? You see these quantum software teams and enterprises, it's built mainly of these experts, and obviously it will be a bottleneck in the future, but we'll talk about the future in a few moments. Right, so you see this explosion of quantum programming languages in the last few years, and please, it's not prioritized, so don't get offended if you like Clsq more than Q# or Forest more than strawberry fields. It's only to show how many quantum programming languages were developed in the last few years. And the progress is amazing. And it's also a good question to ask, why do we need so many quantum programming languages and what's the difference between them? And I'll refer to that in a few moments. But first, let's talk a little bit about the industrial applications. What's the focus today? What they're all trying to develop? So today, quantum algorithms are mainly, at least the near-term quantum algorithms, the NISQ quantum algorithms, are divided into 3 or 4 main groups, right? The first one is simulation and modeling. It's mainly based on the VQE algorithm, and it's very promising in the field of molecular dynamics and finding the ground states of a molecule, optimization problems, mainly combinatorial optimization based on QAOA heuristics, quantum machine learning, which is very promising and has a lot of potential, even though today it's mainly heuristic, QGAN and quantum SVM, etc. And in my view, the most exciting group is the algorithms that are yet to be discovered, right? But we see that even though there is a very small number of known quantum algorithms and heuristics, almost every industry could benefit from that. So today it's mainly finance with portfolio optimization, options pricing, etc. Pharma for drug discovery, automotive for efficient fuels and traffic optimization, but actually almost any technical industry, which is today, well, actually every industry will have a lot to do with quantum computing. Right, so before we move forward, I want to, we have talked about the quantum programming languages, but now I want to emphasize what could be achieved with current tools, with current platforms, with current quantum programming languages, and then to move forward to the limitations and to the future, right? To what we are trying to do in Classiq, and how do we see the future? So three main things could be achieved with current tools. First is gate level coding. So this one that's an example of Clsq, but of course I'll show examples of Clsq, of Q#, of Cirq, but these are only examples. These are three great quantum software development, quantum software languages, and these are only examples. So what do I mean by gate level coding? So this is Python, right? So why do I say that's gate level, right? That's a high level language. But let's take a look at what we really see here. So we see here we produce a quantum circuit, right, with 5 qubits and 1 classical bit. Now we apply on the first qubit on this one and Hadamard gate. And now, which could be done with Python because it's not quantum assembly, we can do a for loop and to apply a CNOT gate on each of these qubits, and etc. You see what I mean? Because on the one hand, yes, it is Python, but on the other hand, you need to know perfectly well which quantum gates, which quantum operations to apply on each qubit. So that is gate level coding by definition, right? So that's first thing that could be achieved with current tools. Second thing is tuning known algorithms. So here you see a piece of code from Cirq, which we apply the QA max cut circuit, and what we are doing is tuning it, right? We define the number of qubits, we define the constraints, the characteristics of the heuristics, and we apply this function. So that's a second thing that could be achieved with current tools. Third thing is, and this specific example is from Q#, is embedding accurate building blocks within your quantum circuit. So in this case, there is a function which is apply quantum Fourier transform. You can just define on which quantum register you want to do that. And right, so that's the third thing you can do. But even though all these quantum programming languages are super beneficial and they're great, we are in a very, very challenging place today, because in essence, quantum software development today is almost an impossible task, right? And the main reason is that we are so limited to this gate level and building blocks programming, right? We every time we want to come up with something new, with a new algorithm, or even to write fluent software, we are struggling with this level of abstraction, and that's very challenging. And probably that's one of the main reasons that the number of known quantum algorithms is so low, right? And that's the current state, and also that's what we are trying to tackle in Classiq. So now let's move forward to the future, or at least to what we are trying to build in Classiq as the future of quantum software. But before we'll talk about our solution, let's see the trend. So obviously, the number of enterprises in quantum computing, trying to develop quantum software will increase dramatically, right? You see this prediction by Gartner that 20% of organizations will be budgeting for quantum computing project in 2 years from now. Obviously, we don't really know if that's true, if it will be 20% or 12%, but we see the trend, and we'll see more and more enterprises in this field and many more quantum software developers. So that's one. Second is the development tools and main methods. So first, we'll see probably higher level of abstraction, right? It won't stay in the gate level, and we'll see, you know, it will be more abstract, exactly in many ways, though it's different, like the classical software stack in the last 50 years. So what you'll see is model-based automation, synthesis of quantum circuits, and also more quantum programming languages, more building blocks, more algorithms to tune. That's a fair prediction. The outcomes, we don't know. There will be many more quantum algorithms. In my view, it's almost arrogant to assume that, you know, we'll in 5 or 10 years from now will remain with a Shor, Grover, HHL, VQE, QAOA, some heuristic of QML. Probably there are more, right? But we don't really know that. And over time, the focus will change from NISQ toward fault-tolerant algorithms. And even today, we kind of see a hybrid approaches, right? Like to embed the Grover iterator within NISQ algorithms, or many other interesting approaches like that. End users are also, you know, that's a great question as well. As we said, the number of quantum information experts all over the world today is very limited, right? So, and obviously there will be needed many more. So I believe that as the time passes and, you know, the level of abstraction will be higher, computer scientists, expert programmers, and of course domain experts will be able to take a more significant part in this effort, while the role of quantum information experts will remain very significant, obviously. Right, so now let's describe a little bit what we are doing in Clsq and how and why we believe that's the future of quantum software. So we bring automation and synthesis to the quantum algorithm design process. Our technology is based on 3 main building blocks. First, high-level modeling, being able to describe the quantum circuit, the quantum algorithm, in a higher level of abstraction. You know, there are many high-level modeling languages in the world, like VHDL, like you know, Simulink, like UML. And what is common to all of these languages, that is, it allows the programmer to define only what is important, what they want the circuit or the, you know, the outlying functionality to do, without being needed to dive into the specific details, because they just can't, right? Imagine designing a computer's chip at the transistor level. We can't do that, right? So we have tools like Cadence and Synopsys, which only allows us to define what we want the algorithm to do, what we want the chip to do, but the synthesis is automated. So that's what we're doing in quantum. And the circuit generator, which is the core technology of our tool, takes the high-level model and synthesizes the gate-level quantum circuit. Another very important part is circuit analysis, and I'll dive into that in a few slides. So let's start with high-level modeling of quantum circuit. So we developed a domain-specific knowledge, which allows the user to incorporate into the input of the you know, into the code, domain knowledge, whether it's, you know, in automotive or finance or etc. Quantum knowledge, of course, it is very important to know how a quantum algorithm, you know, works. It's not a tool for someone who has no clue what superposition, entanglement, etc. And algorithmic vision, right? Because you know what you want to do. You want that you want to create this and this level of entanglement of 100 qubits and to load state preparation, but you don't know how to achieve that in the gate level. So this language enables you to define what you want the algorithm to do. Then the circuit generator, which is based on computer-aided design and constraint satisfaction technologies, takes the high-level model and synthesizes the gate-level quantum circuits, because eventually you need to have the detailed quantum circuit. You can't stay at the high-level model, but this process is automated. The third part is circuit analysis, right? Why it's so important? Because let's say that a 300 qubit circuit was generated. It looks great, and we guarantee that it answers all of your demands. But how can you know that, right? You can't simulate it. You can simulate up to 53, 54, 56 qubits, but no more than that. So it's really important in order to enable you to debug the high-level model to identify patterns, logic blocks, constructs, and sub-circuits to tell you what you actually see. You have asked a certain level of entanglement or some other building blocks, but the analyzer enables you to know that it was achieved. So that's the third building blocks. And these three building blocks are integrated into the Cadmium interface, which, that is a comprehensive solution for designing quantum circuits. And what it really does is, it opens frontiers of creativity, and it enables much more fluent and limitless quantum algorithm development. That's the main idea. Here you see the interface. So what you see here is the high-level model. So you can write this high-level model. What you won't see here is gate-level coding, because the programmer has no clue how will the actual circuit look like. This circuit was automatically generated. And here you also see the quantum assembly that was generated and is totally equivalent to the quantum, to the visual quantum circuit. But what's important is it was generated automatically. And you can tune that, you can change parameters, and that's a radically new way to design quantum algorithms. Here you see some of the results. All of these circuits were automatically generated with our tool. Various use cases, data state preparation, that's combinatorial optimization problem, that's an ansatz for VQE, which are all generated automatically. That's the main idea, and we believe already now we see very, very promising results, and in some use cases it enables our users to achieve results that couldn't have been achieved before by gate level programming. And the main idea is to to building along quantum software developers in order to make sure that's the right tool that will make quantum software limitless. That's the main idea. Actually, I can show a very short demo, Dave, Hanin, if it's okay, and then we can move forward to some questions.
Yes, that'd be lovely. Fantastic. Hanin, you think that's great?
Yeah, we were excited actually for the demo.
Okay, great. So I'll show a very short demo. Of course, that's a very small subset of the capabilities of the tools, but I do want to convey the message of what do we mean. So you see the screen right now, right?
Yes.
Right. So let's start with a very almost silly high-level model, right? What we ask the tool to do here is almost nothing. We just say that we want it to work on 6 qubits. We want the minimal circuit depth to be 1 and the maximal to be 50. Now we press generate quantum circuit. It will take a few moments, and as some optimization is being done behind the veil, and in a few moments we'll see the results. Right. So what we see here is a quantum circuit which does nothing. And why is that? Because we didn't ask it to do anything, right? We only ask it to be with these parameters, and under the hood there were optimizations. So we allowed a circuit depth of 50, but it gave us circuit depth of 1. But now let's tell it that we don't want any optimization, right? We don't need that. Okay, so we generate quantum circuit. This time it will be faster because no optimization will be made. Okay, so we see another circuit, now a deeper one, right? Probably with depth of around 50. And again, it does nothing. So why am I showing that? To convey the message of how different it is than gate level coding. Because here we only define the functionality, but we don't take care of the details. The details are totally automated. Okay, right. That's not a very interesting use case, right? So let's move forward to a more interesting use case. Let's say that we want to do state preparation, to load some probability distribution on 3 qubits. How do I know that's on 3 qubits? Because the length of the probability vector is 8, 2 to the power of 3. And I also allow it to work with 3 ancilla qubits. So the number of qubits allowed is 6. And I demand it to the result to be accurate until 0.1%, which is very, very accurate. And in a few moments, I'll explain why it is so important to be able to relax the constraints, the demands a little. So now it will generate the quantum circuit, which is obviously has functionality, right? It's very challenging to do state preparation even on a small size circuit. And this circuit was generated automatically and answers all of these demands, right? If you run it 1,000,000 times, we'll see this probability distribution up to this level of approximation. But now let's say it's too much for me. You know, that's only the beginning of a quantum algorithm, and I can't use so much resource, right? I need the circuit to be shallower. So let's relax the demands a little bit. Let's allow 10% of error, and let's see what's happening. Let's give it a few moments. Right, and now you see that this is a much shallower circuit, and that's okay because I let it to be accurate up to 10%. But on the other hand, I got a very shallow circuits which optimizes what I can do in the rest of the quantum algorithm or circuit. What we see here in the right is the quantum assembly, which is obviously equivalent to this quantum circuit. And that's two very simple examples, but I think that conveys the message of how different is that and how more, convenient is that than existing tools. And of course, there is a lot of room for imagination, like what is the next building block we would like to model on a quantum circuit, whether it's some entangler or phase shift or resource optimization or anything else. That's the main idea. And yeah, Hanin, Dave, it's I would love to both answer your question and to hear your take on that and on quantum software.
Yes.
Yeah.
Yes. Thank you, Nir. Here. That was fantastic. That's my first impression. I have questions. I have even an airline pilot who has sent me a photo and has a question. I want to talk about what you've done there. It looks like some sort of quantum CAD. I also want to share with you my background where I had to write quantum-inspired algorithms that look like mathematics rather than traditional coding for a portfolio optimization program. And I'm so excited about seeing the graphical representation of what you have there. This is something that brings joy to me. So those are my first impressions. I'm going to ask Hanin to give her words of joy. Then we'll ask Dr. Khan to say a few minutes, and then I'll come back to and schedule the questions that we have here. And we want to give priority, though, to the questions from our studio audience. So with that said, Hanin, I'll give you the floor for your words, then pass it over to Dr. Khan.
Yeah, so great presentation, and I'm really happy to see a demo of the program because as Mr. Dave said, I was happy to see visualization of the circuit, and also it's live, as you're programming, you can see it directly, and also it runs quickly. So that's what I saw. I noticed you can see it immediately. So that's wonderful, and the slide with the programming languages, it's perfect. I think you should post this everywhere on your LinkedIn and on the company because it summarizes other languages. And I also have a question, but when it comes to the Q&A, I can address them.
Okay, so I guess I'm up next, huh? All right.
Yeah.
Thank you, Dave and Hanin. Nir, that was a wonderful presentation. Really excited to see what Classiq has developed. And I think I've mentioned this before to you. I find this topic extremely interesting for two reasons, right? One is that it's extremely relevant to what's going on right now, right? I mean, we are in the NISQ era, noisy intermediate scale quantum devices. These are generation 1.0 of quantum devices, quantum hardwares, right? And to understand how to optimize these hardware platforms, you need to understand what's needed, right? Before you start spending money, right, on the actual hardware, which is a lot of money. So having a device, an algorithm or a tool like the one you just presented is extremely relevant. As Dave mentioned, this looks like a quantum CAD, right? Sort of a computer-aided design tool for quantum algorithms, right? Understanding how they work and kind of preempting what's going to happen before you put the money down in terms of hardware development. The other reason I find it very interesting and kind of dear to my heart is because I wrote a paper 15 years ago. It was my very first paper as a PhD student, scientific paper, which was about quantum logic synthesis, right? So the idea was that somebody walks up, as you were saying, Nir, and gives me a 2 to the 100 by 2 to the 100 unitary matrix, right? Which is going to act on, right, your 100 qubits and says, make it work, make it happen, right? And of course, you have to break it down into 1 and 2 qubit gates. not only because, larger gates can be noisy, but also because there's a very famous theorem that says that sets of 1 and 2 qubit gates are, quantum logic gates are universal. So you can actually implement any transformation or quantum logic circuit in terms of these sets. So it's lovely to see that, that theoretical idea has been actually implemented as a tool. And I admit I tried way back, but being primarily a mathematician, right? Nothing really happened, which is okay, but I am really happy to see that, Classiq has, taken the lead here, and we have a very nice functioning product, in a very important niche of the quantum ecosystem.
That was your 2006 paper, wasn't it, Faisal?
That's right. It was a 2006 paper, exactly. Yeah, a while back. So wonderful presentation. I'll just pass on the mic, I guess, to Dave and Hanin to take care of the questions and answers I think we've been getting. If it's okay, I'll start I'll take the mic back and start the conversation, if that's okay with Dave and Hanin, by raising one question that showed up quite early. Let me see, here it is. It's from Manjunath, which perhaps Nir addressed. This came up, during right after the first break. It says, what areas are you planning to address using quantum computing in the near future? So if Nir wants to take that.
Yeah, so, on the one hand, we can see the industries that are involved in quantum today, which is mainly finance, automotive, aerospace, pharma, energy, chemistry, cybersecurity in a way, but maybe the common ground for all these industries that they have a lot of money and not so much that quantum computing could be helpful specifically for them, because actually it could be helpful for many, any industry. There isn't any industry that has nothing to do with optimization, with material science, with machine learning. So, that's the best answer I can give today, I guess.
Wonderful. Thank you, Nir. Dave, please go ahead.
Oh, well, thank you. Nir, I got excited that you mentioned the airline industry. I agree with your statement that there is every industry who is hitting a bottleneck, I'll paraphrase here, and wants to be able to access to more capability, can achieve that from quantum computing. The thing that's been missing, which I believe you put together through Classiq, Nir, is this ability to more easily code, rather than having to learn particular coding specific to a computer. For example, Qiskit for the IBM Q, and I've spoken to the IBM CTO of Europe about this, of the UK rather. And whereas one hand, there's a team that are looking to program specifically to a particular quantum computer, what you've done here is you're making it easier to be able to code, to move from the traditional quantum coders, Hanin, myself, Dr. Khan, which is more about mathematics, and you're allowing it to move into more traditional coding. You're bridging that gap, and the visual component of that is quite nice. What I have questions myself. I have a photo from a pilot who is on approach to Tokyo, who has a question. But before I go into that, what I want to do, and perhaps Hanin, you might have some questions as well, as you're coding. And by the way, Nir, given the enthusiasm that Hanin was sharing for your software, which is the future, I would say that it bodes well for budding coders. And I had mentioned that Hanin is doing some development work for Darkstar. Now, so what what we were thinking of, Faisal, is for you to go through the Q&A. You identified one, you very nicely passed it back to us. Maybe what we'll do is, if there are any more, or if you want to add some more commentary, you can do that, and then we'll bring it back. So I want to prioritize our guests. We have 80 or so guests that have been on the meetup. Let's try and address them first, and then we'll get to others that have sent me information in advance. And Hanin has her questions and excitement as well. Perhaps we can just do it together, Hanin. So back to you, Dr. Khan.
Awesome. Thanks, Dave. Yeah, so we have quite a few questions. I'll start with the ones that I received in the Q&A section first, and then I'll go to the ones that are in the chat. So we have a question from SK, which says, it's a short, I think, answer to this one. So the question is Cadmium your tool? Is it written by you?
Yeah, so Cadmium is our tool, our interface. It's being developed by our great team, which is built from quantum software developers, quantum information experts, and classical software developers. And yes, again, I guess that the short answer is yes.
Wonderful. Thank you, Nir. The next question is also from SK, which is the following. For quantum circuit, are you using QASM? Where QASM is the IBM, I think.
Yeah, so actually, you know, our output is agnostic. We are compatible with all of the, you know, major quantum programming languages. This the demo that I showed was indeed with quantum assembly, you know, with kit quantum assembly of IBM, also the visualization, but it can, you know, just as easily be any other version of quantum assembly.
Wonderful, thank you. The next question is from Fernando Hernandez, and the question is the Cadmium tool focused mainly on circuit representation?
So I'm not sure I fully understand the question, but I'll try to answer. So what a Cadmium enables you to do is to write, you know, to design your quantum algorithm at the right level of abstraction without, you know, being aware of the details of the circuit. The tool takes this model you create and generates the gate level quantum circuit. And yes, after that, it represents the circuit. And if maybe the meaning, you know, what Fernando meant was whether we are focused on, you know, universal quantum computing, on the circuit representation and not on annealing. So the answer is yes, we focus on digital quantum computers right now.
Excellent. So that's the same as the gate level representation rather than quantum. Okay, good. Wonderful. The next question is from Pablo, who asks, what are the requirements to run the software?
Very, very basic. You can run it on your laptop, and you know, that's what our users are doing. And right now, you know, it's the engine is on the cloud, on the AWS cloud. That you definitely don't need any hardware in order to run the software. Yeah.
Okay, wonderful. The next question is from ZUG. Are the circuits produced by the tool at the logical qubit level as opposed to the physical qubit level?
Yes, so you know, quantum circuits today are agnostic. You know, what a quantum circuit describes is the gate level operations that will be applied on the qubits, but it doesn't really care on which type of qubit will it be applied. So that's on the one hand. On the other hand, if you know in advance what is the physical qubit that you're going to use, it's very helpful because you can embed these specifications into the model and to have the results much more optimally. yeah.
Excellent. So I'm getting a few more questions. So let's look at this one from Vishal, which says, could you please provide us some links to look into cadmium?
Yeah, so right now you can take a look at our website. I will write it down right now. And
Nir, why don't you share the so go ahead and write that down so that we all have it. But then if you would please share your website and walk us through.
yeah, so yeah, I can do that actually, but it will be okay. Just a moment.
I should say, feel free to share your website.
Yeah, so we can do that in a few moments, but basically you don't see it right now. Do you see the website right now?
Yes, yes.
Yeah, great. So the main idea here, right? It's obviously that's a visual representation of the idea, but you see the main idea. The main idea is to take the ideas, you know, and to generate the gate level quantum circuit. What is also interesting here is that obviously what is generated is not only you know, 1 or 2 qubit gates. Sometimes are, you know, a more generalized building blocks are generated by our tool. And the main idea again is to enable the developers to be creative, right? To be efficient, to be creative, to come up with novel ideas, and mainly to express their, you know, ideas, their concepts, their vision in the right level of abstraction. That's the main idea, and we already now see that, you know, it pushes the capabilities, and we really hope that, you know, it will enable the development of more quantum algorithms.
Excellent. Thank you, Nir. One last question from the Q&A, and then I'll pass it on to Hanin, maybe, who can read the questions from the common chat. So the question now is from Tamas Varga, who says, what do you think will be the future declarative or imperative style of high-level quantum programming?
Yeah, that's a very, very good question. So, you know, on the one hand, both declarative and imperative quantum programming languages exist today. You know, in the slide I've showed, so there were both options. In my view, in our view, you know, it will go both ways, and I don't think that there will be a very obvious winner in the years to come. The main idea is to make it more abstract, to incorporate more building blocks, but that's a great question, and only time will tell, I guess.
Wonderful. Thank you, Nir, for addressing those questions. And Hanin, perhaps you can take care of some of the questions, share them with Nir to address that are appearing in the chat.
Yeah, that's perfect. So there are many interesting questions in the chat, and one of them caught my attention because I thought of the same thing. So one of them asked, can you explain what is the Clsq file? So when you showed us the demo, your files had the extension .clsq. So and they say that they guess it is auto-generated compiler language. So as if, like, you know, when you're coding in Python, so your file is .py. So I'm assuming it's because, you know, you're using the software, so it is the extension of the file, right?
Yes, that's the extension of the Classiq platform files, and you know, we could have chosen any other extension, but Clsq was sounds about right. Yeah, so that's the extension.
It's unique as well, so it's really nice. Yeah, so then comes, I think, my question. So when you showed the slide in the quantum programming languages, so you said some people have a preference also, right, for some programming languages over the others. So does the Clsq offer um, multiple programming languages or only one? Do you have a unique version, of like a mixture of programming languages? Like, so this was my question.
Yeah, that's a great question. So actually, in the stack, we are one layer on top of these existing quantum programming languages. We are compatible with all of them, essentially. But right now, our output is quantum assembly of Q sharp, of Qiskit, of Cirq, etc. But as we are one layer on top of that, we have our own language, our own domain-specific language, which enables the user to write the code in high-level model. But actually, there are some great quantum programming languages. I guess that the leading ones today are Q sharp and Qiskit and Cirq also as well. Yeah.
Wow, that's wonderful. I didn't expect this answer. I'm really impressed. Also, I can't wait to use your software one day. So there's also another question. It says that does your tool support different quantum chip topologies, and what backends can you optimize for?
Yeah, that's a great question. So definitely, our output is agnostic, and the agnostic quantum assembly after that could be compiled to any hardware architecture. And as I said before, if you know in advance what are the characteristics of the architecture, let's say that you know that the control Y gate is working very badly on your specific hardware, and you don't want it to be in the circuit at all, you can embed it into the model, and the circuit will be generated in a way that you won't have any control Y gate. So what I'm trying to say is that if you know something about the hardware, it helps. But if you don't, the output is agnostic, so no problem at all.
That's perfect. And Dr. Faisal, shall I go to more questions as well? There are many in the chat.
Yes, let's take a few more. Let's go with two more for now.
Yeah, okay. So there's also one from Elena, and it says, is there any discourse on secure software development for quantum languages or applications? So she explains further. So for example, at assembly equivalent languages, are we expecting issues like buffer overflow still exist?
Yeah, first, it's a very good question, but I think that today, we barely know how to program quantum computers, so we are very far from being able to perform any cyber attacks on them. So I guess that no, I don't know anyone who takes these considerations today, but hopefully in the future, yeah.
Well, I can help qualify that question. Elena is a cybersecurity expert in penetration testing. So she works with Darkstar, and because we have military clients, the concern is that there will be an opportunity for a problem because of the non-quantum quantum interface. So there's actually two parts to the question. One is the one that you've answered. I think you've done a good job there, which is the footprint of quantum is quite small. And in fact, Darkstar has some functionality where just as we partner and show off the great ecosystem and coalition that we've discovered, for example, yourself, we have found other vendors who are able to plug that up, and Elena's in charge of that. So where the actual attack vector is that moment between quantum and non-quantum. And so that's a conversation we can have later. And in fact, we could build in that security to your work, as DarkStar represents the interests of the US military. So thank you, Elena, for that question, Hanin, for asking it. Back to you, Hanin.
Yeah, so there's a question in the chat. Dr. Faisal wanted to address it, which is what areas are you planning to address using quantum computing in the near future?
Oh, Hanin, I think we already raised that question and Nir addressed it.
It was also the Q&A. Yeah, yeah. So also I want to ask something like from my side as well. So for Classiq, so you said that it can be used on any computer or laptop. That's right.
Yes.
Yeah. So also even Mac and Windows. So I wanted to ask you if you are planning to do a mobile app, or like, you know, if it will be compatible with phones later on.
That's a great question. Actually, first, it would be super fun to program quantum circuits on the mobile. Right now, we don't support mobile, but maybe in the future, it will be fantastic. Right now, it works with, you know, with Windows, with Linux, with iOS, but maybe in the future. And just one more sentence regarding what Elena said. In my background, I was a reverse engineer for embedded systems. So I hear you, Elena. It's really important to prevent these breaches, you know, from the first place. But I think that we are not in the place of understanding how to do that enough, right? We are not there yet, but it's super important, and I hope it will happen as the stack evolves.
I'll just add there for Elena, the part of what she's doing is her due diligence with experts like yourself to get your opinion, and then that creates an opportunity for the security industry to focus on that. And Elena's actually looking to see and report back to her president as to what the opportunity might be. And you've done a very good job of supporting that. So there are a number of subject matter experts representing their industry who are listening quite intently to what you have to say. So very much appreciate that comprehensive answer. And I may be just bringing it back to Elena, but thank you for that. And back to you, Hanin.
Yeah.
Hanin, may I suggest one question?
I wanted to ask you. Yeah.
So there's a nice question, and perhaps this could be the last question, because I see we are losing attendees, and it's reasonable because, you know, we don't want to keep Nir for much longer than you know is needed either. One question from SK is about the matrix explosion, right? I think that means basically when the matrix is huge, or you know, circuit depth or width, I guess is what maybe this is referring to. How do you take care of that? Space explosion and matrix explosion as a waveform.
Yeah, so I think that part of the magic is that we don't need to take care of that, right? We can't. You see the Shor's algorithm, right? If you apply it on 5,000 qubits, so it is exploding, right? Because there are 2 to the power of 5,000 dimensions. On the other hand, as the algorithm is scalable, so you don't really need to approach all of these dimensions. And I think that, you know, it's a bit like when you write software for classical computer today. Do you feel that you manage billions of transistors? I don't think so, right? Because there are so many layers of abstraction, so you can just control it without even knowing it's there. So I think that in a way in quantum, it's quite similar. Why, right? We can't write 2 to the power of 300 matrix, but we will probably not need to. That's my view.
So thank you so much, Nir. Thank you, Hanin. I'm sorry I jumped jumped in and took over your
No,
your
no, no.
questions.
I wanted to ask you before continuing if there's something in mind that you have. So that's great.
Okay, wonderful. So Dave, perhaps you can share the picture now from the captain. You're on mute.
In my excitement to share the picture, I got my mute and unmute confused. I would just like to add that was Summit from Cambridge, and Summit Call is a cybersecurity expert, and he's part of the group that we hang out with, where we would speak at Microsoft's Q Sharp meetups through Dr. Kitty. Dr. Kitty Young is where we met. So there's a great group that you have here, near listening intently. So to share the picture, let me move it over to my sharing screen, and let me turn on my share. See if that works good. Screen 1. And let me manually maximize this so it doesn't go too crazy. And hide the vanity photos that I took of us. Now, what we have here is Captain Jeffrey Cole of KLM. He is a 777 captain. He has flown the 737s, I believe. He has flown the 747s. And the 777 is basically the current version of the 747, but with 2 engines. So it's the world's largest 2-engine airplane. In this photo that he sent to me earlier as a backup, was in May 2020, where they're approaching Washington Dulles runway, I think it's pronounced. And the photo is by a Czech captain. So a Czech captain is a captain that audits and make sure everything is fine. And it's such a beautiful photo. You just had to take it. And this is personally shared with Captain Jeffrey Cole, who swore it to us. We're looking at what I found, because I'm a recruiter, is one of my hats that I wear, that I've been looking for a pilot for a while. In that my background includes the airline scheduling industry, and I have a background with U.S. military, as I mentioned. There is a need. Well, let me read what he sent us, because he sent this to me a few minutes ago while he's on approach to Tokyo. Scheduling for airline and pilot scheduling has always been an issue for any airline. To meet the needs of the company, regulators, union agreements, and air crew preferences is a very common issue, and in many cases too difficult to manage with existing software. I am confident that the quantum software systems can offer a much more reliable, dynamic, and efficient scheduling system for all the parties involved. Looking forward to the future, Captain Jeffrey Cole. So what we have here near is a subject matter expert who can guide and visualize what he's looking for, literally from above. There is an additional requirement just below him where the drones are showing up. So there is a need to amalgamate both air traffic control as well as drone control, which is recently from the FAA received an approval. And I would mention that David Wilkinson, our CEO, is qualified through the FAA as a drone pilot, and is in touch with a U.S. Army colonel who we've been speaking about this. As you may be aware, there are some very exciting full-size drones that look like jet airliners designed to launch satellites. This is a conversation that I had with the Department of Defense in terms of first securing, and we have a means of doing that. But then we look to your software, Nir, in terms of scheduling, in terms of visualization for this purpose. I would also add, as I mentioned at the beginning of the talk, there was an interest rather with quantum CAD, which is how Dr. Khan had described your software. And I learned on this talk that you have Cadmium, which tells me that our hopes and dreams of what you represent is likely what's going on. And there is another requirement of the airline. David Wilkinson and myself are speakers for U.S. Air Force and U.S. Space Force conferences. September 30th was our first, and we've appeared a few times since then. What they're interested in us is a bottom to top approach of redesigning the next generation in electric VTOL aircraft and spacecraft. My background in this project is from DARPA, where I worked on some exciting projects many moons ago. And it has come back full circle now where the US Air Force and US Space Force have an interest in this. So one of the expectations they're waiting for us on is a report that says how we can use existing defense contractors who the US Joint Chief of Staff are used to in terms of visualizing a particular field, whether it's a battlefield or whether it's a safety field, that's my term, in rescue operations. And one of the things that we're putting together is a quantum CAD CAM. And when we discovered near that your background and your thrust is in the quantum CAD side, that's very exciting for us because we do not want to reinvent the wheel. We're simply the integrators. And my background also, I'm the chief project officer for Dark Star. I've done this sort of work before for the military, for national security as well. And now we're looking to support that requirement, but from the point of view of the heroes like yourself, Nir. You're the modern day hero that we look up to, as I also look to Dr. Faisal Shah Khan as, and Hanin as yourself. We're the modern version to stand on the shoulders of those who came from before. So in particular, Nir, one of the exciting projects we can talk about later is deploying your software as part of a quantum CAD to mate the Dark Star quantum CAM, computer aided manufacturing, where on another date we can talk about that. Would love to have your thoughts on the whole airline and scheduling industry, and then I can ask you about another question if we still have time and interest. Nir, you have the floor.
Yeah, first, for sure, David, it sounds great. You know, I think that the scheduling problem is one of many optimization problem that, you know, has everything to do with quantum optimization, and the promise is huge. And you see these quantum software teams at Delta Airlines, at Airbus, at, you know, other companies. Mm-hmm. That's what we're trying to do. The potential is very good, and yeah, it would be great to work on that together for sure.
Oh. Well, that's exciting. And again, I'll come back to the visualization that your software represents, because we had sold our partners that we will find one day, we will find a quantum software developer that bridges the gap between the quantum circuitry, something that Faisal and I participated in one of our IBM quantum ambassador resources that was assigned to work with us by the IBM UK CTO. And that was part of the puzzle. And Nir, what you've done is provided the glue, I think. Dr. Khan, can I have your thoughts on that?
Absolutely. I think this is the idea, right? I think the biggest feature that's got me excited about Clsq's product is that there is a logic synthesis component to it, automated, right? Rather than building a circuit, you know, from scratch by guessing, Somebody gives you a large quantum logic gate, we're acting on 10 qubits, 100 qubits, and you automate the circuit that can be built from that, right? That'll implement that particular logic gate. And presumably if it's optimized, that's even better. But I've never seen anything like this before. I did try to build one 15 years ago, but that went nowhere. It's a difficult problem to implement, and I'm really excited to see what Classiq guys have done.
Thank you, Faisal. Hanin, any thoughts? Not to put you on the spot, but what you represent is the new generation of software developers who are trained. Of course, you were trained by the legendary Dr. Faisal Shah Khan, and I've seen the nature of your work. And I think this also represents a very good case study from Nir's point of view of your excitement and of what you like. And we can talk about feedback after the meeting. But what are your thoughts?
Yeah, so actually, like, you can't stop thinking of the applications of quantum computing and quantum software development. So, for airline scheduling, there were many basic techniques, and data analysis, even in R and Python, is used a lot for airline scheduling. And I believe with the quantum software systems, they would achieve much higher accuracy and predictions, I think, at speed, because obviously the quantum chips perform better than the regular computer chips. So that's wonderful. And with what you said with the CAD collaboration, it would be really exciting because using Mr. Nir's expertise in the matter, we can really achieve great things.
Oh, that's lovely, Hanin. Just your enthusiasm is exciting. You talked about both sides with the scheduling. By the way, Captain Cole has permission to bring guests into the cockpit. So this is one of the arrangements that we can make. Hanin, we can do a little selfie in the cockpit there for your friends. I think your friends have showed up. I'm the selfie big on that. I'm a juried artist as a photographer, and Nir, maybe we can bring you along as well. And of course, Dr. Khan. The whole idea is to get the perspective from the subject matter expert as to how do we solve these problems. Hanin, you touched upon quantum has some functionality. What that really is, and I've developed pilot scheduling software myself. So here in Canada, that's what I've done before using Microsoft technology, really about embedding quantum-inspired mathematics to build on scheduling software that's already available. What the opportunity, I think, is, like, if you look at the picture here, and if you can see there's some visualization here. And so what I'm thinking here, Nir, is a multi-stepped process or a multi-layer process where we layer another visualization over the actual cockpit, the cockpit instrumentation and visualization. There's a gap there through a conversation maybe we can have later with Captain Cole and yourself to bridge that gap, and I think that would be a wonderful little project just to see how we can make that happen. So appreciate the positivity, the nodding. So not to take too much more time on this case study, and we did talk about the U.S. Air Force and cybersecurity. Those are the items that I wanted to speak with, and Captain Cole did take a picture on his approach to Tokyo. That's happening right now. So we'll share that photo later on. Now, looking at the time, it's 20 to 1. We had set aside that we speak until 1 o'clock, but we don't need to We don't need to use up all that time. As Dr. Khan, you're feeling the pulse of our members. 2 hours is a lot to ask for on a Monday. So it might be more respectful to wind things down unless there are burning questions that have popped up since then. Dr. Khan.
Thanks, Dave. Well, there certainly people have questions, I'm sure, but let me just tell them to get in touch with Nir directly. They can visit the Classiq company's website and get a contact information. Nir is also available on LinkedIn. You can find him on LinkedIn and go from there. And of course, you're welcome to connect with, send messages to myself, Dave, and Hanin. So I'll just go ahead and share. Well, you can actually look us up on LinkedIn as well. We're all on LinkedIn. I think that's probably the best thing to do. So with that, I think it's probably a good time to end this conversation. Dave, I'll pass the mic to you. Please give us a nice exit.
Oh, thank you, thank you. What I'll do is I'll go last. We'll have closing comments here. Dr. Faisal, you gave yours. Hanin, we'll come back to you for any closing remarks. Back to me again, and then I'll give it to Nir. Hanin, you have the floor.
Yeah, so of course we would love to stay until my time UAE 10 p.m., which is the end of the meeting. But yeah, since people are getting sleepy or tired, so they are free to reach us on LinkedIn, on Darkstar, and also, as you mentioned, with Mr. Nir or Dr. Faisal, Mr. Dave, or me, and we can address any inquiry further. And also, I can see there are some questions on the meetup, so we can also answer that on the meetup page. And also, I would like to encourage them to attend our next upcoming event, which is on 15th of February. So there's a series almost every 2 weeks from MESA. So you can see us at those events.
Right, sorry, let me just jump in really quickly and say that the next upcoming event is also in partnership with the Washington DC group and Association Quantum. Just wanted to mention that. Dave, thank you.
Yes, no, thank you for that. In fact, we're very thankful to Washington DC Quantum Meetup Group that has sponsored and supported the Darkstar theme, in that it's very unusual to have actual clients and practical applications coming from the military. And we had not disclosed that, and they took a chance on us and supported this very serious need. And of course, Association Quantum, that has been supporting us. Association Quantum represents a vast array of both the traditional IT companies like IBM and Microsoft, as well as supporting individuals. I'm very thankful for them. In fact, it's because of that initial support that York University launched its Quantum Computing for Social Impact Group, which I am a co-founder and chair of. So thank you very much for our sponsors. Our biggest sponsor here is, of course, Nir yourself. You have raised the bar by sharing what you have done. As Hanin said, you had a wonderful career in front of you with your background in security, physical security, as an engineer by training. And you took the leap to solve a problem that you saw there. So you were one of the visionaries who made that move. We're very thankful for it. I was absolutely thrilled with the presentation that you gave. Everything was of interest to me. The background was wonderful, and from the hardware right to the software, and then you inspired us. So I'm very thankful for how you have presented this to our group. And so, Nir, I'll turn the mic to you for any closing words, and back to me, and we'll close off this presentation. Nir, you have the floor.
Yeah, I just wanted to say that it was a great pleasure. Thank you for everyone who attended. Thank you so much, Hanin, Dave, Dr. Faisal, and looking forward to more events like this one. Thank you.
Oh, that's lovely. Thank you so much. We'd love to have you more for more events and to follow what Classiq is doing. In particular, Darkstar now, we basically have a project that we want to follow up on. And there's a fan base who's always quite interested. Similarly, we'd be very interested and very thankful for our viewership, which is climbing as I speak, looking at the numbers, if I understand that right. If you have projects, we're very encouraging about those projects. MISA and Darkstar, we're all about helping the ecosystem. For example, promoting and helping if you have a great idea. We all need to work together. All we're asking is for those who want to be part of us to bring your joys, bring your concerns. Let us privately mitigate the concerns so that you're safe. We promise a safe environment. We watch out and we want to see you do well. And now's the time for those with the crazy ideas. I can personally say, come to me with them. So on LinkedIn, come to me, say, I want to talk to you, and let's have a very specific conversation about that crazy idea that you have, and let's make that happen now. This is a group that supports that. Nir, as you saw, is a type of guy who's welcoming these ideas. And in doing so, we were able to do what yesterday people said was impossible. We don't know what quantum can actually do for us because we're now only limited by our imagination. And that is what MISA stands for. Thank you, Nir. Thank you, Hanin. Thank you, Dr. Khan. Thank you to the audience. And I'll declare the meeting closed and look forward to seeing you for the next on February 15th. Just look us up on MISA. We'll see you there.